Hello and welcome to another episode of Mr. Viola's Physics Classroom here on Casual Friday. So, the last few weeks we've been talking a lot about energy, different types of energy, energy transfer, energy conservation. Just want to go over all of that with you now so that we can be prepared for our test next week. So, the first kind of energy we went over was potential energy, specifically gravitational. We talked about ways to represent that. And the very first thing we did was we talked about pie charting. And so if you remember, pie charts at the top are all gravitational. By the time we get to the bottom, they're going to be all kinetic as something falls. So it could be a marker that's falling, it could be a ball, anything that's falling. We start with all gravitational energy at the top, and by the time we get to the bottom, it's all kinetic. Now the important things to see here, the pie is the same size. I'm not a great drawer, but they should be the same size because the pie, the size of the pie represents the total energy. Pi equals total energy. And as we know from the law of thermodynamics, energy is not created or destroyed, so I have the same amount of energy at the top that I have at the bottom. As I go through my fall, that pie starts to converge. So at different points, perhaps if we call this the middle, I have an equal amount of kinetic and gravitational energy, but together they're still equal to the total energy in the system. And then as I get closer to the top, perhaps at the 3/4 mark, I have again a pie of the same size, with kinetic energy taking up 1/4, and then when I'm 3/4 of the way down, most of that has now become kinetic energy as it goes towards the bottom. And then right before it hits the ground, it's all kinetic, it's moving as fast as it's going to go, it's at a maximum velocity. So we can represent energy that way. And what we did with that, we did labs where we dropped a lot of objects down, and we calculated potential energy. And if you recall, the equation for potential energy was mass times gravity times height. So M stands for the mass, which is always in kilograms. G is their acceleration of gravity, which on Earth, we should all know now, is 9.8 meters per second squared. And H is the height that it's dropped from, and we measure that in meters. So a pretty straightforward equation. I'm solving for gravitational potential energy. Other ways, you could also see this written as simply PE or GPE. Those are all mean the same thing as EG. The way it's denoted is really a personal preference. Any of those are fine. When we finished with our gravitational potential energy, the very next thing we talked about was kinetic energy, which if you remember is the energy of motion. Anything that has a velocity or is moving has kinetic energy. And so we had EK equals 1/2 mv squared. Slightly more complicated equation, still pretty straightforward. Keep in mind, only the velocity is squared, not the whole mass in 1/2 as well. So sometimes on a calculator it might be easier to square that velocity first, then multiply by the mass and divide by 2. And again, similar to last time, this could be EK, could also be KE, either one of those, same idea. Similar to the last one, the mass is always in kilograms. So M is my mass, V is the velocity, and I want to have that in meters per second. And so when I do the math, I end up with my kinetic energy, and energy, which we should know by now, no matter what type, heat, kinetic, elastic, gravitational, any kind of potential energy, always going to be in joules. So joules is our unit for energy. One of the nice things about this, and we can kind of reference back to the pie charts. So if I draw just the top and the bottom of something falling, I can set these equal to each other. So we did something watching the skateboarder fall. We did some stuff with roller coasters where the gravitational energy at the top is the same as the kinetic energy at the bottom. And so I can go ahead and substitute my equations. So I get mgh equals 1/2 mv squared. Those masses cancel out. And I end up with something like this. Now it should make sense that the masses cancel out because how fast something falls doesn't depend on the mass. We learned that a long time ago. In the absence of air friction or air resistance, whether you drop a feather or a bowling ball, they're going to fall at the same rate because they're accelerating at the same rate. So it doesn't actually matter. All that matters for how fast it's going to go is how high it was and what the acceleration of gravity is on that planet. So this is an option if you were trying to solve a problem where you need to find how fast they're going or how high something was dropped. This is certainly a relationship that you can make between the very top where something was let go and the very bottom when it was just about to hit the ground. Afterwards, we looked at a lot of elastic energy. So when we looked at elastic energy, we looked at EEL, and that was 1/2 kx squared. And so in this case, K was the spring constant, and our spring constant is in newtons per meter, and then X is the elongation of the spring, and we measure that in meters. So if you remember, we did a lab with this where we put some weights on the end of a spring and we saw how far it stretched, and the distance it stretched was our elongation. We could use that to solve for our spring constant if it was unknown, which we did a few months ago with the related equation of F equals kx, where we had elastic force, which is just the weight on the end of the spring. K with our spring constant, and then we could solve for the elastic energy. What we found in that lab was that the more weight we had on the spring, the longer the elongation and the greater the elastic energy that was held in that spring at that time. The spring constant, as the name suggests, should always be constant. Also, if you were doing some work with a problem, and perhaps there's a bungee jumper and you wanted to find how far the spring is stretched, you can pie chart this as well. You get something like gravitational energy at the top, and then at the bottom, instead of being kinetic energy, I actually have it all in elastic. The bungee is fully stretched. I put all that energy into the bungee, which is elastic energy, and I could have something like mgh equals 1/2 kx squared. Perhaps I'm trying to find out if it's going to be safe to bungee jump. I might know the spring constant. I know the mass of the person jumping. I know how high we are. I need to know how far it's going to stretch. If it stretches too far and hit the ground, obviously bungee jumping would be the last thing that you do. So in this scenario, I could once again set these equal to each other, because in this scenario, the gravitational energy at the top is being completely transferred to elastic energy at the bottom of that bungee jump. And then the final thing that we talked about was heat. So heat, for some of you, we had an equation of Q equals mc delta T, where Q was our heat energy, M was our mass. Be careful this time, it's in grams, not kilograms. It's the only thing we do where this is in grams. C stands for specific heat, and it's in joules per gram degrees Celsius. Specific heat is basically telling you how much energy does it take to heat up 1 gram of that substance by 1 degree Celsius. For water, it's 4.18. It's different for every object, every item. So delta T is change in temperature, and we measure that in degrees Celsius. As a quick refresher, 0 degrees Celsius is where water freezes, 100 degrees Celsius is where water boils. So we might be looking for heat energy, we could be looking for the specific heat of something, maybe we're looking for the change in temperature. It's all going to be based on algebra, rearranging this to solve for whatever variable that you need. In addition, we talked about the 3 ways that heat can be transferred. And those were conduction, convection, and radiation. Quick examples of each. Conduction is if I'm touching something, if I touch the board, it feels cool on my hand because I'm transferring heat energy into the board. So my hand feels cooler because I'm losing heat energy to the board. Convection, probably familiar with a convection oven. Bakeries use them. Also a sea breeze would qualify as convection. And then finally radiation. The most common source would be the sun, which basically warms the whole planet. I don't know, basically it does warm the whole planet. And you could also consider the greenhouse effect, or any heat that is radiated down. Best of luck on your tests. Thank you for watching.